All right, and good evening. Tonight, what we're going to be talking about is what the shapes of individual molecules actually take on. You are drawing them very well probably by now, but what you want to do is you want to be able to figure out what in 3D does it look like. Okay, so what happens is that we've got this theory, and it's called the Vesper theory. So valence, shell, electron pair repulsion. And what that does is it actually tells you the shape, it's used to predict in chemistry, the shape that an individual molecule will take on. And what this actually means is because electrons are negatively charged and you're putting them by other electrons, which are also negatively charged, they want to be as far away from each other as possible. So they're going to take on a shape in 3D where these electrons are as far away from one another as possible. So let's look at an example. All right, so if we were to just draw methane, which is CH4, okay, we would draw it probably like this, okay? And if you look at this, the angles that the carbon to hydrogen or hydrogen to carbon to hydrogen forms looks like it's a 90 degrees. But this is when it's drawn on 2D, which is the only way that we can actually draw it on a piece of paper is in 2D. But our world exists in a 3D format. So instead, what will actually happen is you've got this carbon and it's going to go up, and let's say that I'm going to draw hydrogen, okay? But then what's going to happen is that the one guy is going to go kind of like in the back, okay? And this is going to form like a more of a tripod. That's a really bad drawing of it. It's kind of like a tripod look, whereas each of these ones on the outside are your hydrogens. And what ends up happening by making it be able to pop out, they are able to take on an angle of 109 degrees. So if the elements or these electrons could choose between having an angle separation of 90 degrees or 109 degrees, they are going to take on that 109 degrees because of the valence shell electron pair repulsion, which means that these electrons want to be separated as much as possible. And this shape is known as tetrahedral. Okay, and you will have to have all of these shapes memorized. All right, so what is the effect of lone pairs on shapes and have on the angles? So if we looked at methane, okay, methane, which was that CH4, okay, looks like this, and we were to compare it to, let's say, ammonia, which is NH3, so NH3 looks like this, okay. If you analyze it, it has each central element has 4 things coming off of it. The carbon has 4 hydrogens attached to it. The nitrogen has 2 hydrogen or 3 hydrogens attached to it, but it also has this one lone pair. So if you look at it, it's connected to 4 separate things. Okay, and what ends up happening is, according to the Vesper theory, this forms 109 degrees. Okay, but what actually happens is that this angle between the hydrogen, nitrogen, and hydrogen actually forms 107 degrees. And you're like, what? If I'm attached to 4 things, why does it all of a sudden change sizes? Well, if you want to think about it as like sitting on a bus, okay? And these guys, this nitrogen, right, or the carbon, let's say, has basically one electron at all times between these bonds. Okay, so we're pretending that it has the 2, but in reality it basically only has the 1. If you look at this ammonia one instead, what you get is that, yes, the bond between the nitrogen and hydrogen is sharing 1 electron, but that lone pair on that nitrogen is 2 full electrons on that nitrogen at all times. And because if you look at this has 5 electrons, whereas this has 4 electrons, you're going to have to divide up the space a little bit more. And lone pairs tend to take up more space because they have those 2 full electrons on that central element at all times. Okay, so your angle actually decreases the more lone pairs you have. And what I always do is I associate it with getting on a bus, okay? So, or like in an airplane. And so you have a certain amount of seats. Let's say you're in a 3-seat row and you have you sitting down there, and let's say somebody who is larger comes down. Well, what's going to happen to your space if they're sharing your same row? Well, because you only have a limited amount of space in your row, they are going to take up disproportionately more than if you were splitting it evenly. That's exactly what happens with this ammonia, okay, is that these lone pairs right here, and a lot of times what they do for these lone pairs is they'll draw like a big circle with the 2 dots on it. If you want to show just spacing, that just represents a lone pair. But what happens is that these guys, because they're so big, they actually force these other bonds down more and closer to each other because they only have a certain amount of space and those lone pairs take up more. So if we look at now water, okay, water has it looking like this. Yes, it also is attached to 1, 2, 3, 4 different things, but in this case it has 2 lone pairs. And what does that do? Well, it actually makes the angle between that oxygen and that hydrogen 105 degrees. So as you can see, it goes from 109 to 107 to 105. So the more lone pairs, you basically go down 2 degrees-ish. All right, so these are the different shapes that you're going to have to understand and know, and you will have a sheet on this if you don't already. What this shows is how many things, the electron groups is how many things is it attached to, okay? So it doesn't show how, it's like with the water. Water, that oxygen is attached to 1, 2, 3, 4 different things. So you'd be talking about these guys, okay? The bonding groups is how many literal things is it attached to, like elements wise. So for this water situation, it'd be attached to 2 different things. And then lone pairs, you'd be counting how many on the central atom. This is all dealing with the central atom. It's not dealing with any other elements that in the structure. We're only dealing with the central atom. So in this case, it's this guy and this guy, so it would have 2. So its geometry would form on this tetrahedral shape, but its actual one is bent. And if you look at it, it forms this like lovely looking like this shape. That's the water molecule right there. All right, so let's just try some practice problems. So carbon is attached to 2 different electron bonding groups, and it has 0 lone pairs. So I'm going to look for something that's attached to, on the bonding group, 2, okay, with 0 lone pairs. And so that would be a linear structure. BR, there is no central, BR2, there is no central one, so you just choose one, and that one is just attached to 1 different thing. So if you think about it, what's any shape, what's the only shape it can take if one thing is attached to only one other thing? Well, that would be linear also. Okay, so that would be linear. All right, NH3, it is attached to 1, 2, 3 things. So we're talking about it's attached to either this one, and that's it. And how many lone pairs does it have? It has 1 lone pair, so it would be taking on a trigonal pyramidal shape. Pyramidal. I change it. I say pyramidal and pyramidal all the time. Change it all the time. And what that is, it literally looks like a little tripod, okay, without the top part. And then we've got methane, which is that CH4. It is attached to 1, 2, 3, 4 things, so that would work. And hopefully this one works, but it has 0 lone pairs, so this would be a tetrahedral. And not only is the electron group geometry, which is with the shape if you included all the lone pairs and everything, tetrahedral, but because it doesn't have any lone pairs, it's molecular geometry, which is what we really care about. We care about these columns, basically, these 3 columns primarily. It too would be tetrahedral. All right, let's try water. So water is attached to 2 things. So we're talking about this guy and that guy, and it has 1, 2 lone pairs. So that would be that bent shape. Okay, and then we've got H2CO. So H2CO is attached to 1, 2, 3 things. So for that guy, we're talking about this one or that one. And how many lone pairs? Well, it has 0 lone pairs. So we are talking that it is trigonal or trigonal planar. And what that means is that it actually forms a triangle on a single plane. So this is forming a 120-degree angle. It's all on the same exact plane. PCl5 is attached to 1, 2, 3, 4, 5 with 0 lone pairs. So you are talking that is trigonal bipyramidal. Trigonal bipyramidal. And then the last one, SF6, is attached to 6 different ones with 0 lone pairs on that central atom, and so it would form that octahedral shape. And if you look at the octahedral shape, you'll notice that it forms a square, okay, and then it also has 2 prongs coming up. So this forms a line right here, whereas this guy forms a square. So they actually have different angles. So if this is the square one, this is 90 degrees. And then these guys are, and then these are also 90 degrees. So everybody's like 90 degrees from each other. All right, hopefully you have an understanding basically of how to identify the shapes. For a while you will be given these, but you will have to memorize all of these molecular geometries and how they associate with how many atoms they are bonded to and how many lone pairs they have.